So let's assume we have a random variable x which has some distribution f, some distribution. This may or may not be Gaussian, but this f, this random variable x has a distribution f with some mean, with let's say population mean, with population mean of mu and population standard deviation of sigma. Okay, this is my population mean, this is my population standard deviation. Now let's assume I have a sample. Okay, let's assume I have a sample from this. I have, let's say, x1, x2, so on and so forth, x10, right? This is a sample of size 10, of size which is often written as n equals to 10. Okay, so this is a sample of size 10. I have 10 observations. So let's take the previous example where we sampled heights of people and we use these numbers, right? 180, 162, 158, 172, 168, and I'm just writing down the numbers here so that you can play with these numbers later when I show some results. Okay, so these are my 10 observations of heights of people in centimeters. Okay, let's assume we don't know the distribution. It could come from any distribution with some population mean of mu and some population standard deviation of sigma. Now let's ask a question. Okay, the question that we have in front of us is, what is the 95%, what is the 95% confidence interval for 95% confidence interval of mu? Okay, so this is a very simple question. I'm estimating the 95% confidence interval of mean, of population mean of the random variable. Okay, that's the title of this video here. The confidence interval for mean, which is mu, or population mean to be precise there, of a random variable. Okay, the random variable can come from any distribution. Okay, so the question we are trying to answer here is, given this sample, given this sample of size 10, right, of size 10, what is a 95% confidence interval of mu? How do we compute this? There are two cases for this. Let's go case by case. Okay, so case one is, let's assume that somebody gave us the population standard deviation. Let's assume somebody told us that sigma equals to 5 centimeters. This is the case where we know population standard deviation. We know this. Okay, we'll see case 2 where we don't know population standard deviation. Imagine if we know this. Okay, if you recall, we had learned a theorem called central limit theorem, one of the most powerful and beautiful theorems in statistics, in probably whole of mathematics itself. What would we say? We said that if I take my sample mean, my x bar is my sample mean. Okay, my x bar is my sample mean. What is my sample mean? It is basically 1 by 10 summation over I equals to 1 to 10 xi, because I have a sample size of 10, right? What CLT tells you is that whatever this distribution is, as long as the mean and variance or mean and standard deviation are finite and valid, that's what CLT says, right? It says that my random variable x bar follows normal distribution with the same mean and with the standard deviation of sigma by root n. Okay, this comes from central limit theorem. This is literally what central limit theorem says. To again put it in words, it says that my sample mean follows a Gaussian distribution. It follows a Gaussian distribution with the mean equal to my population mean, right? And its standard deviation equal to population standard deviation divided by root of n. If I have a sample of size n, if this is computed using a sample of size n, here my n equals to 10. Let's not forget that. This is literally what your central limit theorem tells us. Now, since I know that my x bar, okay, follows this distribution, I can confidently say that my mu, my population mean, okay, lies in the interval x bar minus 2 times sigma by root n, comma, x bar plus 2 times sigma by root n with 95% confidence. Okay, this is exactly what we saw earlier, right? When I told you that if I know the distribution of a random variable, I can tell what is the 95% confidence interval trivially. If I know, especially if I know that it's a normal variate. What I'm doing here is nothing but this is basically mu minus 2 sigma and this is mu plus 2 sigma, okay, of this random variable. Now, this is where CLT is super useful. Whatever, again, remember, here I'm not assuming that my x is Gaussian or anything. It could be any distribution, which is very, very important. It could come from any distribution as long as it has a finite mean and a finite variance and or a finite standard deviation. As long as that is held in place, I can take a sample of size n and I can compute the 95% confidence interval using this. Okay, now when I use this data set, that we have here, my x bar turns out to be 168.5 centimeters, right? In this case, remember, what all things do we need to know to find out these exact values? I need to know x bar, and I know x bar because I have all these values. I can just, so from this sample of 10 heights that I've given here, I can quickly compute my x bar, and my x bar is 168.5 centimeters. Okay, my root of n is very simple. My n is 10, so I have a root of 10. Now here we assume that we know the population standard deviation, which is sigma, right? So since I know that sigma equals to 5, I just make sigma equals to 5 here, right? So I know my x bar, I know my root n because I know that my sample is of size 10, and I know the sigma value. Now if I just input all these three values in here, I would get a confidence interval which looks like this. So I can say, using this sample of size 10, I can quickly say that my population mean lies in the interval 165.34 centimeters and 171.66 centimeters with 95% confidence. Right? I just literally put in all the places. I have my x bar here, I have my root n here, my sigma equals to 5. I just put in a calculator and got these values. Now here, remember, here we have made a big assumption here that I know my sigma. This is a big assumption I made here, that I know my standard deviation of the population. Okay, here we are also applying one of the most beautiful theories in statistics called central limit theorem. Next comes the important question. I think case 2. Let's write it down. If we do not know sigma, or sigma is nothing but population standard deviation, right? It's sometimes unfair to assume that you know population standard deviation, right? If you do not know that, what can you do? And you have a sample of size n. Okay, here your because even if you apply central limit theorem, okay, you can apply central limit theorem. Of course, central limit theorem will perfectly work, but you don't have the value of your sigma. How do you compute now? If you don't have your sigma, you can't simply apply your central limit theorem. Okay, so in this case, where you do not know your n, we use something called a t distribution. It's also often referred to in statistics as student's t distribution. Okay, so what student's t distribution, the theory says, is that your x bar, your sample mean, right? This is your sample mean. Okay, your sample mean follows a t distribution with n-1 degrees of freedom. This is called degrees of freedom. I'll show you. This is called degrees of freedom. Your x bar follows a t distribution. This says that it follows t distribution with n-1 degrees of freedom. Now, once you know a distribution, you can compute the 95% confidence interval, right? But it's not so straightforward for t distribution. Let me just pull up my, sorry. Okay, I was using some code to compute some values here in our, that's okay. So let's move. This is the Wikipedia page for students' t distribution. Okay, so the t distribution looks like this. It looks somewhat like a Gaussian curve, but it's not exactly a Gaussian curve. You should be careful of that. Okay, so your V, it has only one parameter here. This parameter is the degrees of freedom. Okay, so as the degrees of freedom increases, the peakedness, so as you go from orange towards black here, right, your degrees of freedom is increasing. As your degrees of freedom increases, the student state distribution gets peaked and peaked, right? This whole distribution literally was discovered, was created to compute confidence intervals. The whole distribution, so to student state distribution was literally studied and computed to estimate confidence intervals, to estimate confidence. One of the biggest applications of student state distribution is estimating confidence intervals of mean of a random variable, when the population standard deviation is unknown. This is one of the biggest applications of student state distribution. We'll not go too deep into this because, of course, if you know the distribution, you can find the 95% confidence interval and apply all of the math. Okay. There is one problem with the approach that we discussed in this video, right? We were trying to estimate, in this whole video, we were trying to estimate confidence interval of population mean of a random variable, right? For which we had two cases, right? Case one was that sigma is known. Sigma is known. We used CLT and then Gaussian distribution, right? We use CLT and Gaussian distribution. Case two, where sigma is unknown. So sigma is unknown. In such a case, we used T distribution with n-1 degrees of freedom. This is only for population mean. Now, the big question that I always had when I was learning these as an undergraduate and a graduate student was, how do I estimate the confidence interval for sigma of a random variable? Or how do I estimate confidence interval for median of a random variable? Or the 90th percentile value of a random variable, right? Because for mean, central limit theorem will work very beautifully for you, but it doesn't work as easily and as beautifully for sigma. Similarly for median or 90th percentile. So if I have statistics like these, if I have parameters or statistics like this that I want to compute, like all these are interesting statistics. Okay, mean is also an interesting statistic. If I have statistics like this, how do I estimate confidence interval for them? None of the two techniques that we just discussed will work. Okay, for that, with the advent of modern computing, as computers became much more powerful, where we could do simulations, there is a whole new school of confidence interval estimations that are studied. Okay, those are called bootstrap-based confidence intervals, which we'll learn in the next video. Okay, to be very frank, with modern computers, with modern statistics, with modern computational power that we have today, bootstrap confidence intervals are extremely powerful, and I can compute confidence intervals for any of these statistics, not necessarily just for mean. Even in the classical statistics, even the pre-computer statistics, there are some ways to compute them, but they're not very, very strong. They're not easy. Now, there is one great trick called bootstrap confidence interval, the single trick with which I can almost compute the confidence interval for all of these statistics very, very easily. And it's a single beautiful computational method that we'll discuss in the next video.